Welcome back to the course on how to build an AI agent from scratch. In the last video, we introduced the concept of memory. An agent should be able to remember basic things so it doesn't have to learn everything from scratch every single time you create an agent. And in that video, I mostly talked about simple memory architecture. For example, storing a raw dump of the entire conversation in a file and then fetching that file when you create a new agent. I talked about maybe some smarter improvements, maybe storing separate different files, and in each file you'll just store a small amount of relevant information that the agent can fetch when it needs to. However, if you have a 100-page document or a Harry Potter book, or you're trying to do the law and there's a bunch of case law you have to ingest, then accuracy is critical. You need a way to store and fetch all of this information when you need to, and a basic markdown file just isn't going to cut it. In this video, I'm going to be talking about advanced memory architecture, and I'm going to focus on two different approaches. Number one is using a vector database, and number two is using a regular database with semantic information. Both of these are different but important strategies for building long-term memory in your AI agent. Let's first start with the vector database, and specifically, I'm going to be focusing on a technique called Retrieval Augmented Generation. Let's talk about that. Retrieval Augmented Generation is how you search through a large number of documents using vectors. First, you need a vector database like this. A vector database is simply a database that stores numerical embeddings or vectors. And these vectors are the meaning of the inputs. So instead of searching text like you would in a regular database, you are searching for the similarity in vector space. This sounds really vague, but let me give you a concrete example. With this image I generated using AI. So first, the parts of Retrieval Augmented Generation are, first, you want to take all of your inputs and transform them into vectors and store them in a vector database. So we have this cat, put it into an embedding model, it'll form this cat vector. We have this other cat, put it through a vector database, it'll store this cat vector. This is actually a kitten, this is a cat, but they're similar but not exactly the same, as you can see by the numbers. Next, we have a dinosaur, and this dinosaur is pretty far away from this cat, but it's sort of similar-ish, but it's pretty far away because they're not the same thing. And then finally, we have the moon. This is way off. It's not even kind of close to any of these other things that we've stored. So these things are stored in the vector database, and then at runtime, we'll have a query. Let's say our query is cute animals. We'll literally search through vector space to find the things that are close in space, and then return them back to the user, and then we'll put it back into our system prompt as information. We just inject it into the prompt as retrieved information, or not even in the prompt. We can also put it in the conversation. The point is, this information will be given to the language model. Now, you don't need to know how all this works under the hood. You don't need to know about cosine similarity and the different types of similarity algorithms, because most of the time, this is done for you. You know, there are managed vector databases that do a lot of this. You can just create an account. You also oftentimes don't even need a specialized vector database. You can use something like Postgres with pgvector, or something like MongoDB. And if you have a short amount of vectors, you can just store it in blob storage. You don't really need a vector database, but you do need some way of retrieving these vectors quickly if you're implementing Retrieval Augmented Generation. So this is one way of storing a large amount of documents. It relies on transforming the inputs into vectors and then doing a similarity search. Another more advanced technique is just to simply store information in your database with tags that you can query later. Here's a concrete example within my app, Nexus Trade. This is my agent summary data model. After an agent run, we store the iteration start, iteration end, and also certain things like some semantic insights and some procedural lessons. Also, for each portfolio, we store things like what the instrument type is. If it has options, what's the option structure? How good did this strategy actually perform? Which tickers were involved? And we store that for every single portfolio that is generated. That way at runtime, if you say, I want to create another option trading strategies, we can query for similar strategies that you've already created, that already did well. And now we have a great starting point. We don't have to start learning everything from scratch because we've already learned a lot of these lessons. So this structure is actually injected at runtime if you use my app Nexus Trade. And this makes it so the agents improve over time automatically. You're already injecting insights that have been proven to work into your agent at runtime. And so this just improves the agents. Now, here's a curveball question. How do we know our AI agents are actually improved? What evidence do we have to suggest that our agents are getting any better at all? Are we just going to read through the agent and make a judgment call? Yeah, this looks nice. This looks good. Yeah. Not for a production AI agent. That's not going to make you pass the AI native software engineer interview at Meta. You need a systematic way of evaluating your AI agents. This is so important and something that most people don't think about at all. In the next video, I'm going to be talking about agent evals and how do you know your agent is doing what you want it to do.